Let's start. Thanks very much, everyone, for coming. Today, it is my pleasure to introduce Daniele Gaggero. A bit of background, he did his PhD at the Università degli Studi di Pisa in Italy and continued to do postdocs at CSIC-Universty, at Grata, at the University of Amsterdam, and at IFIC in Madrid before obtaining a tenure-track position at the IFIC in the University of Valencia. So please, Daniele.
Thank you very much for the invitation. We'll talk about work mainly on connections between black hole phenomenology and dark matter searches. And today we'll mostly talk about searches for primordial black holes with multi-messenger techniques. So quick introduction about the topics and context. So we are aware of the existence of black holes at different scales. For example, solar mass black holes from 8 solar masses up to more or less 100 solar masses that serve them very well in the gravitational wave channel, but also in the X-ray channel as part of X-ray binary systems, for example. Then we are aware that supermassive black holes exist. For example, they are typically located at the center of galaxies and we observe them up to very large redshifts. Then we are maybe we are confident that intermediate mass black holes may exist in the universe, which is sort of in between the mass ranges in between solar mass and supermassive. And all this, how does this black hole research field connect with the dark matter? On the other hand, we are aware that dark matter exists in the universe. There are pieces of evidence from the galactic scale to the galaxy cluster scale to the cosmological scale about the existence of this elusive substance that makes up most of the mass in the universe. And black holes themselves are a dark matter candidate. So we know very little about. I mean, there are many ideas about what are the candidates of dark matter. We know very well, for example, some of the properties. We know very well the density, both locally and on cosmological scales. There are many ideas that were proposed about the nature of dark matter itself, and I typically show this diagram with this 90 order of magnitude from very light absolute particles to actually primordial black holes. And so compact objects, in particular black holes, are one of the candidates that were proposed, actually the heaviest candidate that was ever proposed as being a constituent of the dark matter, maybe subdominant part, maybe the bulk of the dark matter itself. And this idea has been discussed for more than 30 years, almost 40 years now. And what are these objects? So this would be a new class of black holes that are not of astrophysical origin, that are not formed at, for example, the end of stellar evolution. They would instead form in the very early universe, actually deep in the radiation era during the first second of the life of the universe, and they should originate out of small-scale fluctuations, large amplitude small-scale fluctuations that are much smaller than the ones that give origin because of structure, typically originated during inflation. So the idea is that if you have a mechanism during inflation to have an enhancement of the power spectrum at small scale, when the perturbation re-enters the horizon, there can be a collapse of the perturbation and a primordial black holes can form. The mass range is very large. I mean, so we can have primordial black holes spanning a huge mass range, and actually this is the mass range for primordial black holes to be a dark matter candidate. You have to be at least in this range of mass, because otherwise they wouldn't be stable over the whole Hubble time. They would evaporate to the emission Hawking radiation wave 4 present time, and they can be as massive as the region with 4 solar mass and even more. So the questions that we deal with today are, okay, if primordial black holes are part of the dark matter universe or all of the dark matter universe, then how can we detect them? In particular, we mostly focus on 2 channels, and in particular, the first channel, well, we are releasing a paper really today, so probably we spend a bit more time on this. So the idea is whether you can detect in the future primordial black holes by searching for an anomalous rate of high redshift gravitational wave merger events. So that's the scientific question. That's the one avenue for discovering primordial black holes. On the other hand, I will also talk about how we can detect primordial black holes by observing the radiation emitted by baryonic gas, ordinary gas, accreted onto them. This would be more related to galactic. On the other hand, this would be related to the cosmological distances and to the very high redshift. So yeah, this is the plan. And yeah, there is also a complementary research line which sees the problem from another angle, which I will not talk about, unfortunately, but it's in the backup slide. So, and we can talk offline if someone is interested. So one can use black holes not as a dark matter, not as a tool to discover dark matter, whatever is your favorite candidate. So black holes can be exploited because they can originate overdensities of dark matter around them. So whatever is the dark matter candidate, one has the possibility to check for anomalies in the waveform emitted, for example, by in this system, the comfort object orbiting in the black and look for anomalies in the waveform due to the presence of overdensities of dark matter around the mass of the black hole. So actually, there are many connections. So black holes can be a dark matter candidate themselves, they are primordial, or you can use black holes as a portal towards the discovery of dark matter, whatever is your favorite dark matter candidate. So the problem is actually very, very complex. But moving to primordial black holes, again, so typically we deal with this kind of plots, and we do phenomenology of primordial black holes. So we give typically now upper limits, since we haven't discovered primordial black holes yet. So typically on the y-axis, we have the fraction of dark matter in the form of primordial black holes. And on the x-axis, we show the mass scale. You see, huge, it's very large, it's very wide. And so this plot is very crowded with a lot of upper limits. Each of them come with assumptions, are heavily debated. So this is a quite rapidly evolving field. And in particular, this mass range here is particularly interesting because there were some upper limits that were very recently proposed. And here you have the possibility to detect a subdominant population with future experiments. So either improve the upper limit or make a detection. So this is a particularly interesting window, the one I will focus on. So few solar masses up to tens or even hundreds of solar masses. And also these bounds are questionable. So it's quite interesting to
There are also bounds coming from supernovae in that region. Remember some paper I said, in Malakari, they are kind of reducing between precise and romance numbers. Any reason why you're not including them?
Well, actually, this plot, there are way more bounds than each of them come with assumptions, with uncertainties. Now, in that specific case, no, I didn't have a particular reason not to include it, but just for the sake of simplifying the problem, because otherwise this plot would become completely unreadable. But is it's not stronger than the last one?
They don't allow for 100% of matter. So they really
in this video, you
the ones on
no, yeah, you're right. But I think the strongest one is still the one from the merger rate. So yeah, okay, no, I see your point. Yeah, okay, but I think this is the strongest bound. The merger rate bound is still the strongest, if I'm not.
you're right.
Okay, don't know, but I don't. So the bonds that are not showing so I don't have a strong argument against the bounds that are not shown. It's just to simplify the visualization.
Okay, can I ask a question? Sorry.
Yeah.
So in the left part, there's the bond due to the evaporation. Why is the line not horizontal?
Yeah, this is the reason is that, okay, black holes that are lighter than 10 to the minus 18 for a massive, they would have evaporated already. So they couldn't form, given the evaporation rate due to the emission of Hawking radiation, they couldn't form their matter today because they would have, so that's the reason.
No, why is it not horizontal? Why does it?
Because actually the evaporation rate is a function of the mass. So in this region, so you could have, actually you could set even more bounds by studying the radiation emitted, the Hawking radiation emitted. So even if the part of these black holes could have survived, and then you can still look for the radiation to have emitted by those who have survived and place a bound. So it's a smooth transition between the vertical line and then, so you can see, yeah, exactly. A fraction of them could have survived, and you can So this is the region I would talk about, and yeah, and these are the two avenues towards detection that I would like to discuss. And for detection, and also ways to be properly. So merger rate, in particular merger rate at high redshift, as a window, possible avenue towards detection, and then X-ray radiation from accreted matter. So yeah, let's start. Yeah, of course, just like we mentioned that all these bounds come from an assumption that typically refer to monochromatic mass function. So there is a debate in the literature whether highly non-trivial mass functions can potentially partially evade the bounds. So it's a very complicated story. And in some cases, some peculiar mass functions can partially evade some of these bounds. Still, I think making 100% of their matter is very, very challenging. But all this, most of these bounds were derived under the assumption of a monochromatic mass function, so for each pass. Yeah, just let me mention, let me flash that the subdominant population is still important. So even if primordial black holes are not all of the dark matter, it's still very relevant to look for them because they are an important problem per se, depending on what is the fraction of the dark matter they amount to. Because the reason is that, for example, if primordial black holes were to be discovered even in a very subdominant portion of the dark matter, there are interplays with other dark matter candidates. So, for example, there is an inconsistency between the existence of primordial black holes and the existence of WIMPs. So, if primordial black holes were to be discovered, WIMPs would, you expect WIMPs to cluster around them. So, you expect to have a lot of gamma ray radiation that would overshoot by far the amount of gamma ray radiation we observe. So, you could set extremely stringent upper limits on the WIMP annihilation cross section. So, there are interplays. So, if you were to discover their matter, they could also solve other problems. If, for example, they could explain the existence of supermassive black holes at very high redshift. So there are many reasons why primordial black holes are very relevant. They could also explain something about the physics of inflation. They are directly connected with it.
Yeah, can I ask you, so how can you distinguish a primordial black hole from another black hole? Is it just due to rates or like all these probes? How do you...
That's $1 million question, actually. And most of what I will, okay, a big portion of the talk will be precisely about this. So in particular, I will show how, depending on the redshift evolution of the merger rate, you can clearly distinguish astrophysical and primordial population, for example. That's one of the ways. So yeah, that's exactly what people discuss. I will show. Yeah, so for example, this is the channel of the argument towards such detection that I will mention, and it's actually looking for merger events in this period of the cosmic history before reionization and after recombination. It's called the Dark Ages, where the universe was basically there were no stars. The universe was basically only consisted only of neutral hydrogen, basically, and helium in small quantities, and like that. And in this epoch, you don't expect to have any astrophysical network. So in this epoch, if you were to detect with, for example, Einstein telescope merger events associated to redshift that are compatible with this epoch, then that could be really a sort of smoking gun. Of course, this seems easy, but as I will show, it's highly non-trivial to really pinpoint an event and associate it to this epoch. It's a very distant epoch, so it's highly non-trivial to do it in practice, but the idea is very simple. The idea is that you go to an epoch where you don't expect to have any astrophysical mergers. That's as simple as that. But in order to exploit this channel, you have to understand how primordial black holes form binary systems, how these systems evolve, how they merge, and so you need to build a framework to understand the evolution and the merger of primordial black hole binaries. But the goal is to really, have a model for the redshift evolution of primordial black hole binaries and understand how to distinguish them from astrophysical ones. So actually, primordial black holes can merge. Actually, the primordial black holes can form binary systems, and then the binary systems can slowly inspiral and eventually merge, exactly as astrophysical binaries do. And typically, most of the signal that you expect would be due to binary systems formed in the very universe shortly after their formation. So the concept, the idea is that you form primordial black holes very early on in the history of the universe, deep in the radiation era, and shortly after, pairs that are close enough can overcome the Hubble flow. So the gravitational pull can overcome the Hubble flow, and they can form shortly after the formation binary systems. Those binary systems would be very compact, actually also very eccentric, as I will see that I will show in a moment. And those would be the binary systems that are expected to contribute to the merger rate. Then, yeah, they can also form binary systems later on. For example, if primordial black holes exist, they can find each other in a halo, in a structure that is already formed in a dark matter halo. They can, due to a close passage, they can lose some energy due to the emission of gravitational waves. They can form a bound system and form a binary that can contribute to the rate. But this effect, so binary systems that form shortly after formation, where the density is very large, when these objects are all basically together, should be the most important contributor to the rate. So what we need to do is build a formalism to understand how these binary systems are distributed in terms of orbital parameters and predict how they evolve, how their merger rate would evolve in redshift. So that's what we need to do to understand this potential signal. So typically, yeah, you have a probability distribution for these primordial black hole binaries that is well studied under the assumption of having an initial situation where these black holes are basically homogeneously distributed, and you only have the Hubble flow and the gravitational pull, nothing more than that. And the thing is that basically you really have only these two ingredients. So you have a pair. This pair would be taken apart by the Hubble flow, but then gravitational pull overcomes, in some cases, the Hubble flow, and you form a binary systems with a small angular momentum that is provided by the torque exerted by the surrounding black hole. So you have a probability distribution in terms of angular momentum and, say, major axis for these primordial binaries that can be computed just under these two assumptions. So you start with a random unclustered distribution of primordial black holes. You may have decoupling from the Hubble flow for a given pair, and the angular momentum acquired by the binary system is due to the torque exerted by the surrounding primordial black hole. So under this very simple framework, one can construct a probability distribution for the primordial binaries in terms of same major axis and dimensionless angular momentum. And this probability distribution would be towards very eccentric binaries, because in absence of surrounding PBHs, the problem would be completely linear. So each pair would be just taken away by the Hubble flow, and then the gravitational pull wins. So with this at hand, and with a formula which is very well known for the merger time as a function of the major axis and dimensionless angular momentum, you can derive a probability distribution for the merger time as a function of time. So in principle, you can compute the merger rate at each given redshift under this assumption in the case of primordial black holes making any fraction of the dark matter. Of course, this can be applied to any fraction of the dark matter. And this is already, so yeah, this is a visualization of a problem again. You have a pair, the pair is taken away by as redshift decreases by the Hubble flow, then decoupled from the Hubble flow, it starts to oscillate to form a binary system, its own spirals, and it eventually merges. Of course, there are some complications that I think I will skip, but this already gives a lot of information, because, for example, by comparing the prediction for the merger rate today with the data, you are already able to set an upper limit on the abundance of primordial black holes. So this is one first result. If you take your merger rate computed today as a function of the fraction of the matter from PBHs, and you compare with the data, with the rate inferred by LIGO and Virgo, given the observations today,
you also take into account the spin heat.
No, in this case, no. I mean, all this formalism is completely transparent. Actually, to spin, you expect them to have very low spin or null spin at formation. So yeah, it doesn't enter the game in this formalism. It's not near, but it's reasonable to assume that.
But if we the PB is spinning so fast, then can affect the structure.
But still, I don't think, yeah, but I don't think that this would change. I mean, I don't see a reason now why a small spin at formation that shouldn't be there could impact this bound by a lot. I don't see an obvious, I think this is very stable with respect to this assumption. And so by comparing with the rate today, you can detect, you can place an upper limit on the abundance of primordial blackness reflection per matter. But then the nice idea comes from the redshift evolution of this merger. That's where things become interesting, because you have very different behaviors from if you compare the redshift evolution of primordial black holes within this framework, within this model, and the expected unavoidable background due to astrophysical binaries. The two behaviors are very different. I mean, the evolution of with redshift of the astrophysical black hole rate is expected to trace the star formation history. So it's expected to rise up to redshift of roughly 2, and then you expect to have a steep fall off, and you expect to have a null rate at very large redshifts. By large, I mean larger than, say, 30, the formation of the first 30, depending on where you believe the first stars form, but you expect them to fall. On the other hand, the primordial black hole rate is expected to steadily increase as a function of redshift. And the reason is that the probability function peaks at very eccentric binaries, which are the ones that merge faster. So given this probability distribution peaked at very low angular momentum, very large eccentricity, those are the ones that merge earlier on. So you expect the rate to be an increasing function of redshift. So one may think of exploiting this window between the redshift 10 and 100, which is a very fast redshift, as an interesting region, as a target for Einstein telescope to distinguish primordial and astrophysical binaries. Of course, it's not, I mean, this is easy to explain, but there are various complications. First of all, there are complications with respect to the modeling, because there are many effects that can impact this kind of simple model. On the other hand, there is a huge experimental, I mean, we have to assess whether Einstein telescope is as accurate at those high redshifts as to distinguish primordial and astrophysical binaries. So how much time do I have?
About 15, a bit more.
Okay, so let me go, okay, well. So
No, actually almost 20, because we started a bit late.
Yeah, so let me go actually to the main result that I wanted to show. That is a paper that we won't write like today. Yeah, tomorrow actually. We're going to post on that today. So it's an assessment of the capability of Einstein telescope to do this exercise. So this plot is the same, just shown in the detector frame, but it's the same plot. It's the merger rate of primordial black holes, astrophysical black holes versus the merger rate of primordial black holes. And so we want to assess whether this is feasible, whether even a small fraction of primordial black holes can pop up at very large redshifts and manifest itself with an anomalous rate at very high redshift. And to do so, we applied a mock data technique. So we really simulated the response of Einstein telescope by generating mock data for different fractions of their matter in the form of primordial black holes. To do so, we had to rely on a model, the model that I discussed with you, so the model a model for the evolution of the merger rate as a function of redshift, draw a redshift from this theoretical distribution, then draw position, polarization, inclination of each event randomly, and for each random event taken from this distribution, compute the strain, and by convolving with the functions that parameterize the response of the instruments, that are called the antenna patterns. So we have the strain of the gravitational wave for each mock event. We have the signal to noise ratio that can be computed given the noise power spectral density associated to Einstein telescope. So for each of these events, we have the luminosity distance, the redshift, and we can compute the
signal-to-noise ratio. There are a lot of technicalities. We can also take into account the effect of lensing, which is, provides an additional uncertainty. But the most important ingredient is the instrumental error on the distance, which is typically taken as inversely proportional to the signal-to-noise ratio. So louder events will be able to be detected with smaller error on the luminous distance, as is quite intuitive. So this is one of the key ingredients. So for each event in this mock data set, we are able to compute the signal-to-noise ratio and the uncertainty on the luminous distance. So we created this mock data catalogs. I think this plot shows very well the situation. So as a function of the distance, you have here you have the uncertainty. Here we have the threshold for detection that corresponds to a signal-to-noise ratio of 8. So here you have a population of astrophysical black holes, how it would look like in this plot. You see that increasing distance corresponds to larger errors. And then you would have a population of primordial black holes popping up at very high distances. And so now the question is, how can it be distinguishable, and how low the fraction of primordial black holes can be in order to be effectively measured, detected, and really measured. So we want to assess this. So with this framework, with this mock data, we can start to do statistical analysis. So we can apply statistical methods and assess whether Einstein telescope can distinguish or not. For example, this is a very simple way of putting things, cut and count. So you can divide the mock data into bins, the low redshift bin and the high redshift bin, and you can compute at which fraction of their map in the form of PBHs you can start to see a significant excess with respect to the background in the high redshift bin. And this plot is quite nice. You see that already, at a fraction of PBH of 2 times 10 to the minus 5, which is extremely low, way lower than the current constraint, you could already detect primordial black holes with a quite large significance, above 3 sigma. This is the 3 sigma level. So because you would have an anomalous rate of events in the high redshift bin, and you can clear the detection. So you would have detectability already starting from 2 times 10 to the minus 5 in terms of FPH, in terms of fraction per matter in the form of FPH. And if the fraction is as large as 10 to the minus 4, well, which is still very low, this method would be very powerful. So you would have a significance way above 10 sigma. So the Einstein telescope, despite the enormous distances that are involved, is so sensitive that it can detect a population of primordial black holes this small in terms of the diameter with more than 10 sigma significance. This would correspond, you see the red scale here, to hundreds of events above a redshift of 10. So this population would manifest in terms of 100 anomalous events above a redshift of 10, and it could be actually significant. So yeah, another more formal method is a proper likelihood analysis, which defines an ambient likelihood. You do full Bayesian, and this is really able to assess the measurability of these parameters. So you can do more than that. You can really want to assess how precisely Einstein telescope can measure this FPBH parameter. And so we produce, this is basically the main result for this part. And so you have on the x-axis the FPBH, actually the fiducial FPBH that we use to generate the mock data set, the real FPBH if you want. And on the y-axis, you have basically for you have every vertical slice is your posterior, is how well you can measure FPBH, and you have the reconstructed value from the likelihood analysis. So you see that for values of FPBH larger than 10 to the 5, you can have a very good measurability. So with already 1 year of data taking of Einstein telescope, you can measure the dark matter fraction primordial black holes with this precision, 35% precision at 1 sigma, and then especially gets even better. So we demonstrated Einstein telescope is really extremely sensitive, extremely powerful in this kind of exercise. And with 10 years of data taking, you can not so much. error bar even lower. So this is, I mean, the capability of Einstein telescope 10 years are amazing. So you can go down to almost close to the 2096 in terms of fractions of that. But, of course, then, so basically we demonstrated that we will be, in the future, we'll be systematically limited. So that's nice. So in order to measure, so the statistics will not be a problem. And so all the debate about whether an anomalous rate could be associated with primordial black holes will be all about systematics. So there are many. So it will be all about systematics in the modeling. For example, the role of clustering, the role of the mass distribution can play a role. So this curve can have some systematic depending on your assumption, for example, initial clustering, and then systematics due to the background. So we kind of demonstrated that in order to detect the subdominant population, the problem will be completely systematic dominated. And in particular, one of the big systematics will be probably the presence of a bump in your background at redshift around 10, 12, due to population-free stars. This is probably the elephant in the room if we were to detect an anomalous rate at high redshift. So all the research should be concentrated on this, but at least Einstein telescope has a very nice science case, and anyway, any anomaly can be either the detection of the population-free bump or the exotic detection of primordial black holes.
One question for the astrophysical black holes in their simulation, they used just star formation history, or
yeah, actually we did a bit better than this. So we considered two models that kind of bracket the uncertainty. Yeah, for example, we chose a fiducial model that is directly traced by the models for the star formation rate history that is traced by catalogs of galaxies in the infrared or in the ultraviolet. But also GRBs can be used as a tracer. Actually, for early star formation, that's a better tracer because star formation could actually happen in very small halos that are not traced by catalogs. So GRBs were shown to be an alternative tracer of the star formation history. There is a systematic here, but yeah, we did the analysis in both cases. But still, yeah, you can't exclude the presence of some structure here that would interfere a little bit with.
And you mentioned clustering, so you think that, I guess it will influence for redshift 10 a lot, but afterwards maybe the orange, also the primordial black hole should be contaminated by that, right?
True, that's true. Actually, late time clustering in particular, because you primordial, yeah, that's a very good point. Yeah, this could actually have it. Actually, we quantified this. So I probably there was no time so I didn't skip this slide, but yeah, that's quite interesting. So primordial black holes can form clusters because, I mean, shot noise, the initial shot noise can be amplified by gravity. That's what gravity does. It amplifies any inhomogeneity. So you can form clusters over the ether of the universe of primordial black holes. And in particular, the smallest clusters can undergo core collapse, can be unstable due to thermal instability. So all the binaries that fall in these small clusters would be perturbed. And you see this formula. It is a fourth power of A and the seventh power of J. So even a small perturbation can alter a lot the merger time. So if your binary system ends up in a cluster and it receives additional torque, then it will never match because you add the angular momentum, it will never match. So you have to remove from your computation all the binary systems that end up in small halos that undergo core collapse and become dense enough to perturb the binary systems. This is true. This is an effect that is more relevant for late redshift. So this results in a suppression factor of the rate that is redshift dependent and also dependent on the fraction of PBHs. But we followed some reference papers for this, which provide the formalism to take into account this. And we saw that, yeah, the impact of late time clustering suppressing the merger rate, for example, today, is relevant only for very large fraction of their matter in the form of primordial black holes that are already excluded by the present day bound. So this could, in principle, be a relevant effect, and it seems not to alter the prediction for the subdominant population that we're looking for. But still, yeah, it's quite tricky. Yeah, this has to be, I mean, this is just one formalism. It has to be taken into account. And also initial clustering can play a role. Actually, initial clustering can alter again the merger rate, but this for example, there are some claims that a very broad mass function can come with initial clustering that can alter the prediction. So yeah, systematics in the modeling and systematics in the astrophysical background, but the Einstein telescope is powerful enough to make a great measure of really tiny fractions. So maybe, yeah, probably I can give a glimpse of the other elements.
You still got like almost 10 minutes.
Okay, it's fine. So I can, yeah, so yeah, just to give a glimpse of another completely complementary channel to detect the primordial black holes. This is electromagnetic, and it's not far away, so it deals with our galaxy. So the reason is, okay, so the thing is that accretion is very powerful. So, and we live in a galaxy with a lot of baryonic gas, clouds of gas, in particular close to the galactic center, you have a massive population of clouds of interstellar gas. And we know that accretion is very powerful in converting gravitational energy into electromagnetic energy. So you can have emission of multi-wavelength emission. You can emit radio waves and X-rays when matter is accreted onto a black hole. So one potential channel consists in looking for the radiation potentially emitted by accreted matter onto primordial black holes that might be a part of their matter, so might be, for example, in our galactic halo as well. Here, okay, since I want to give a glimpse, I will go to the result. The thing is that at the moment, what this method, this channel, again, can be used to set an upper limit. So the main result now, for now, is an upper limit. And the rationale of this upper limit is the following. So you want to compute the number of X-ray and radio sources that were to be expected if primordial black holes were there, and you don't want to overshoot the number of known sources, for example, radio sources near the galactic center measured by DLA, and X-ray sources, for example, in the hard X-ray band measured, for example, by the Blue Star experiment. So this channel naturally produces an upper limit by requiring not to overshoot the number of observed radio and X-ray sources. And this is the upper limit, actually, that we show the most updated one, which is quite strong. It goes down to 10 to the minus 3. Again, it's similar to the LIGO bound. So again, you exclude a large portion of parameter space, but again, you have a channel for a science space probably for future experiments in both radio band and X-ray band to detect a subdominant population, which, as I mentioned, is very relevant because there's no particular reason why primordial black holes should be all of the dark matter. So the problem of searching for primordial black hole and searching for dark matter can be decoupled. The primordial black holes could amount to any fraction of the dark matter, and the problem, this search is interesting per se. Only, of course, you always parameterize the abundance of primordial black holes in terms of the abundance of dark matter as a reference. But this upper limit is actually quite strong, and I think this is really a new way to indirectly search for primordial black holes, which has some similarities with the problem of, for example, with direct searches for WIMP. So here, for example, you may touch some astrophysical floor, because at some point you go down, you're so sensitive that you end up dealing with the unavoidable background of astrophysical black holes that are there. So you end up being so sensitive that you can touch some astrophysical floor. Then you may wonder whether this bound again can be evaded, for example, with some peculiar mass functions, since this bound comes with a threshold effect at low energy. So the accretion rate at low mass is not large enough to set a bound anymore. So for example, the radial of the threshold here in this ray, at some point you will get a threshold as well. So these are basically some questions we are really working right now. So probably future lines of research. How much time do I have? Just a
few minutes.
Oh yeah, okay. So just let me give a glimpse of the astrophysical floor. That is, I think, quite interesting. So the thing is that there is an interaction between the primordial black hole search and the isolated astrophysical black hole search. So these are two fields of research that are connected, because on the other hand, people working on astrophysical black holes are dealing with the problem of of how to detect the huge number of isolated astrophysical black holes that are in our galaxy, that are not detected yet. We only detect in our galaxy the black holes that accrete from a companion star. We only detect these are the X-ray ones. We observe them very well. We have catalogs, but then we expect to have 10 to the 8 isolated astrophysical black holes in our galaxy just from stellar evolution. And this is the big iceberg that we can detect with this channel. And so there is an interplay between the primordial black hole search in this channel and the search for isolated astrophysical black hole in this channel. That would be a natural floor to this bound. So actually, it would stay here more or less in this diagram. So a floor that we are really touching. So a natural question to address again is the astrophysics. Is again where how would be the prediction for this astrophysical pattern. So we tried to assess this with a paper, and yeah, probably that's the last plot I will show. A couple of plots, very crowded, but the message is that we moved to model the astrophysical population of black holes in the galaxy. We did this exercise. It's a very uncertain problem. It really depends actually on one parameter, that is the average velocity of these black holes, especially in the central region of the galaxy. So it's really uncertain. You need a parametric study, but the main result is this solid line, probably. So the number of expected X-ray sources from the inner galaxy can be of the order of few tenths of sources, which is comparable with the number of X-ray sources that I was showing you before. So if we go back to this catalog, so basically we are showing that a part of these X-ray sources detected by new star near the galactic center could be already could be due to accretion onto astrophysical black holes. So so a part of these sources that could be astrophysical black holes and could be primordial black holes as well. So if the fraction is low enough. So the primordial black hole search hits this astrophysical floor, and studying the astrophysical floor, we realized that a portion of these sources already detected by new star could be already isolated accreting astrophysical black holes. That is one of the 10 type of sources of Turner's. And this is, well, a wonderful science case for SK. But if you go from this to a radio band, if you go to the radio band will the sensitivity in the radio band will increase by 1 order of magnitude with the SKA. That's the big new thing in the radio astronomy in the next decade. And so the typical flux, the radio flux that you expect as a function of the velocity of the black holes for astrophysical black holes would be very easily detected with SKA. So again, yeah, as Einstein telescope could detect hundreds and probably thousands of events at high redshift due to primordial black holes, SKA can measure and can detect again hundreds probably of events associated to astrophysical black holes in the galactic center or primordial black holes. So here the challenge would be to distinguish and discriminate between populations. And then, yeah, well, just like we mentioned, final note that peculiar mass functions can evade these bounds. So all these bounds, this is a final message that maybe is also interesting. So all these bounds have to be taken with a grain of salt. For example, if whenever the bound depends on some effect that has a threshold at some mass, there can always be mass functions that you can easily find in the literature and motivated by physical arguments and come to evade the bounds. For example, this is one exercise that we did recently. So we consider a mass function taken from this paper that shows multiple peaks in the mass that are connected with interesting events in the early history of the universe that should facilitate the collapse, the formation of primordial black holes. Actually, each peak corresponds to a pressure drop in the early universe due to the change of the equation of state. For example, the big peak here is due to TCD phase transition. So if you consider this, and all these events could facilitate the formation of primordial black holes because you have a pressure drop, a drop in the radiation pressure associated to all these events. So these multi-peak mass functions, you can show that can evade the bounds. So, for example, the X-ray and radio bound at low mass can be evaded, and this would be the U bound partially evaded with this more complicated mass function. So yeah, just to give a glimpse of all this field of research, but ask you some questions, but maybe it's time to go to the conclusion, so it's very late. So yeah, I think I have demonstrated that primordial black holes are very interesting. They could constitute a portion of the dark matter in the universe, and there are a couple of avenues towards the possible detection of the subdominant structure of dark matter before primordial black holes. One, actually, firstly, I showed the anomalous rates at high redshift that could be potentially associated with the subdominant pollution from the black holes, and then possibly a radio and X-ray emission associated to black holes in near the galactic center as another channel detection.
Yeah, question? Yes.
Yes, thanks for your very interesting talk. We would like very much that all that matter is in black holes.
That would be nice.
I have a question of principle that perhaps should be raised, and it's the following. Primordial black holes with mass less than 10 to 15 grams should be seen. We should see them by now exploding because of Hawking radiation, and there are lots of constraints on that, and we don't see those primordial black holes. So we can deduce from that either Hawking radiation, well, people don't believe, but it might be, or there are no primordial black holes, because if there are no primordial black holes with mass less than 10, 15 grams, why should we have primordial black holes with mass greater than 15 grams?
That's a good question. Yeah. Actually, well,
so there is a prior, there is a very heavy prior on these.
Okay, let's see, because it really depends on the physics of inflation, right? I mean, actually, there are many models that predict primordial black holes only in the high mass range without having without interfering too much with this region. And the reason is, well, the inflaton potential can always be engineered so that you have an inflection point associated to your preferred mass scale, and this inflection point would produce a peak in your power spectrum.
Yeah, I understand that, but then you can do anything.
No, but that's
you can put your inflaton predicting small mass black holes, high mass black holes, etc. But in a broad context, generic context, I think it's a very heavy prior against.
But actually, these searches are very agnostic of both mass function and the mass scale. I don't see why this should be such an heavy prior to discard. No, I don't see that, because really, I mean, there are so many scenarios for primordial black holes. It's a huge. I mean, like with now that's the direction where dark matter searches are going, right? For each candidate, you have. It's very hard to set. It becomes harder and harder to set priors. So, I mean, from my point of view, as a phenomenologist and as an astrophysicist, I'm very agnostic on the underlying. But that's my point of view. But I think I don't know. That's probably a matter of opinions, I think, because it's very hard. I mean, there are so many models that were proposed, but I mean, whether these models are natural or, I mean, this is an endless debate. But this affects all dark matter searching for all candidates, right? Because I mean, in the WIMP case, it's the same situation. So the natural WIMP in the TV scale is probably excluded by them. But I think the dark matter problem is so. I mean, now that I think the idea is really to no stone left unturned, probably in the dark matter searches, because it's really, I mean, there are infinite models. So that's at least my take.
Thank you very much. I have two questions. One is you mentioned the 2.3 stars, and that you have a remnant of the black hole, and so you have a kind of signature. You should be able also to give some kind of constants of, let's say, the black hole reduced to be a nice pattern for the dark matter constant.
I mean, if you were
about it. Yeah,
so
one of the images you showed that involved the next one. Yeah.
so add them to the background module.
You should be able to look out for the fraction of that coming from the proportional.
Though that's something, okay, yeah, okay. This is something we want to study. We haven't studied it yet, but this needs to go to the literature and understand that.
Okay.
So one thing, for example, I don't know yet, but we are about to look at that, is take all the literature about predictions for the amplitude of this bump, bracket, the uncertainty. One has to, yeah, this has to be done. This hasn't been done yet, bracketing this uncertainty, but
Another, maybe not every question, without that, there would be the merger of two black holes and see the signal. But I will expect, and you say you are trying to find like, oh, sorry, I didn't say the problem. You don't, in some scenarios, you can use the black holes as a way to draw the clouds of, let's say, the accent or whatever.
Yeah.
But I would expect the signal on the top of the merger to be very weak. Maybe.
you mean, but this is the other, the part I didn't cover.
The merger, and then you are looking to a signal within the signal, right?
Yeah, but that's a very different,
Yeah, it's a different question.
it's a different, no, but in that case, the observable would not be the rate. It would really, the observable is the waveform itself
Yeah, but still.
of a given
You
event.
have a lot of legal, I imagine it's a lot of things than just let's say the signature itself.
Oh yeah, in that case you have
You are looking to a very tiny gravity effect, probably, or whatever, on top of it.
on top of a signal that we, but it would be on, okay, so just to give you, this would be anomalous waveforms in this context. Of,
Okay.
No, but it would be, I mean, on top of a signal that LISA is expected to measure very well. That's the thing.
Oh, okay.
Because this other thing would be in the context of LISA. This would be looking for anomalies in the waveform, but we expect LISA to measure very well, like for 5 years, many cycles. So no, that's another, but that's another.
No. Okay.
Do you think it's possible to separate also from environment between astrophysical and primordial black holes or not? Meaning astrophysical maybe more surrounded by star formation gases and stuff.
In principle, that would be a nice way, but I think it's quite feasible because this would require a position reconstruction of the event. But it's very okay. Gravitational wave storm is very challenging.
Maybe with the X-ray.
Maybe if you if you have some, okay, this is all a dark, a dark Sainian approach, so you don't have any counterpart. Yeah, if you were to have some electromagnetic counterpart, but what I mean, it's very hard to have one. I don't see an easy way to use this. But actually, the position, the localization in the sky is very challenging, right? So, and in order for it to be so good to discriminate, I don't know.
Any other questions? Well, if there's no more questions, let's thank our speaker again.
If you enjoyed the video, like and subscribe.